A warm good evening to everyone present in today's bootcamp. I'm Abhinav and I work as a BMS algorithm development engineer and also as a cell testing and characterization engineer at Decibels Lab. So today we are focusing on one of the, you can say like advanced concepts or at least a little bit more in-depth concepts of cell modeling that is called as PNGV modeling of a lithium ion cell. So in actually some of our previous webinars and bootcamps, we have covered some other like basics of cell modeling. So this webinar will not be going that basic into the cell modeling. So instead, we are going to jump into the like directly into the mechanics of the model itself. So some introduction will be given to like some concepts related to the cell modeling, some approaches, and then we go off into the PNGV advanced modeling approach. So, like today's webinar content, we begin with introduction to the necessity for cell modeling. So, just to get a background on why cell modeling is done. So, whenever we model a cell or an electrochemical system, what all the things we need to consider and what are the approaches that need to be considered. So, these are like the different like contents and approaches that we need to first like look into, have some review on this. Then we proceed into the very specific components of the model of the cell that we are considering today. Then we consider the Simulink uh, environment where we have developed a model at Decibels. So this is a simple, like you can say, uh, low complexity model that has been developed. So that will be reviewed. And then we'll go into the simulation, just look into a simple trial simulation, and then we go to the results and conclusions. So before we begin with this webinar, I'd like to ask my colleague Vinayak to please share the preliminary like poll questions. So like just to get an idea on how well versed are you with cell modeling, whether it's a totally new concept or it's something that you have considered before in your careers. So yeah, Vinayak, I request you to please share the uh, poll questions. Yeah, and I request everyone that is participating today, please do take at least 2 minutes to fill out this form. So we'll just quickly discuss the relevant answers, and then we'll move to the required topics. So here, the first question, what approaches to cell modeling? So of course, that is left for the audience to explore. Then what is meant by ohmic resistance? So ohmic resistance is always associated with the cell materials. So like when we consider the bulk materials that is present inside, which actively participate in the functionality of the cell. So that is the like material that usually offers a resistance to the flow of ions. So that is why it is called as ohmic resistance. So next, what process of a lithium ion cell does an RC battery model represent? So mainly we are representing all the processes inside of the cell as electrical elements like resistors or capacitors, things like that. So later on we will see like how they're built. So fourth one, which model type is preferred for simplicity? So always it is electrical models. So most of the time they are like very good in terms of like simplicity, and they have a good balance between like simplicity and accuracy, which is why most of the times like many people they go for electrical models. Then, so what is meant by time constant of the RC circuit? So this is a slightly advanced concept. So basically it has to do with the response of the cell. So when we apply some load, some electrical load, like some current, some discharge current or some charge current. So it is some like something to do with the time associated with the response during that application of the load. So that later on, actually, it will be used to characterize the entire cell and then to derive something called as RC parameters. So we will see that actually later on. So yes, so with that, we will proceed forward to the content of today's bootcamp. So just before we go forward into our topics for cell modeling and things like that, some very basic and simple introduction to what is PNGV. So PNGV is basically it's a global platform which has been introduced by the like American automotive associations and things like that. So PNGV stands for Partnership for a New Generation of Vehicles. So basically, this was introduced in 1993 with the main focus to improve passenger transportation efficiency. So their idea was that they wanted to reduce the amount of dependency on petroleum, basically diesel and petrol. So they wanted to do this by adding like more types of energy sources for the vehicle. So either by converting it into hybrids or adding some fuel cells to propel the vehicle along with the IC engine, or also by changing the like control systems of the engine in the ECU such that the engine is much more efficient, and like some other like experimentation like that. So thereby the outcome is that they would reduce the impact of passenger vehicle emissions into the environment, right? So yeah, it was introduced in 1993 with the collaboration of three American automotive companies, that are General Motors, Ford, and Chrysler Corporation. So these three together, they collaborated and they invested in like these many types of like R&D points. So namely being like researching alternative fuels and also any like alternative energy sources. So like as mentioned before, hybrid cars, like either fuel cell hybrid or battery hybrid. So going also into material research for energy sources. So for other types of materials, like for example, for the fuel cells or for the batteries. So what kind of like materials can be used, which is the most efficient, most cost effective, most affordable, things like that. So in with this concept, or rather with this context, we then read into the PNGV type of cell modeling, because the PNGV battery testing manual proposes a particular type of uh, equivalent circuit model, which is known as PNGV cell model. So that is our main focus for today, and it is developed in the focus to make the battery modeling and simulation as effective as possible, so that it represents the realistic behavior of the cell. So we will see that in the upcoming like slides. So what is the necessity of cell modeling? Why do we choose that approach? Like for what purpose do we go for cell modeling? So it's only for the sake of understanding the different types of approaches and why we do this. So how do we define modeling? So basically, any process we take and we represent them utilizing mathematical expressions, and that's what we call as modeling. It could be of any type. It could be using softwares like ANSYS or computational fluid dynamics, or even things like NXPro 3, or things like CATIA V5 or SolidWorks, anything. So not just that, even other softwares are there like MATLAB and Simulink, or you can even use COMSOL. We can even use like Altair. So there are so many softwares which we can use, where we can use like linear models or any algebraic expressions, functions, differential equations, partial derivatives, integrations, things like this, to represent any system's functionality. So we can take a few examples. So like for example, we can consider a simple experiment which many people would have studied this in their school or in their college as well. So when you take a spring and you displace it with some load and you measure how it extends, you will notice that the amount of force applied is directly proportional to the elongation, or you can say extension of the spring. And that you can see here on the left side, like basically there's a linear graph that represents the behavior. So this is represented by like a simple linear equation, y is equal to mx, right? So we know this is a very simple equation. So this represents uh, the behavior of the spring. So in like simple words, you can say the spring is modeled utilizing this equation. So y is equal to mx, right? So this is a case of a linearity where there is not much like deviation from uh, like the center line. There is not much deviation, and there is not much, you can say, like influence in terms of the non-linearity. The slope doesn't change much, things like that. But when we consider like more advanced systems, like specifically electrochemical systems, you can see on the bottom there is a graph that represents the change in resistance with respect to the cell state of charge. So these are like complex behaviors which are like purely like based on the chemical processes, and these processes, you cannot represent them utilizing such like linear models. It would not truly reveal the nature of the cell, the complete behavior, the mechanisms, all this. So for that purpose, we represent all of these utilizing like combination of these, or at least a combination of two of these, like things like polynomial functions and derivatives or differential equations, to represent each of these processes. So with that understanding, when we represent a cell, an electrochemical system, a lithium ion cell, as a mathematical model. So what are the advantages? What are the benefits of doing this? What are the outcomes we get? So there are many outcomes, and collectively, this helps in making batteries and battery management systems much more reliable for passenger vehicles. So not just passenger vehicles, any electric vehicle approach or any electric vehicle type or model that we wish to implement all this into, but definitely this is very much beneficial. So basically, the main idea of developing such a lithium-ion model, a cell model, is to observe how well it is able to replicate real-time cell behavior, right? So that is the main goal of making a cell model. So necessity is basically defining uh, the most important goal, that is to represent real-time behavior. So how do we define real-time behavior? That is to say voltage behavior. So there are so many things like open circuit voltage, terminal voltage, charging or discharging, or highly dynamic scenarios in drive cycle voltages. So how it changes with respect to time, with respect to age, with respect to temperature, with respect to SOC, and so many things like that. It can be studied. So of course, it depends upon what approach we choose. Depending on that, you can define accuracy, or you can define like how close it is to real-time behavior. Then the thermal behavior, which is very important because temperature has a very huge impact on the like cell age, you can say the cell performance characteristics and things like that. So then degradation in capacity, when we come to the conditioning of the cell, basically the age of the cell. So here, age is like very heavily impacted because of many operating conditions like the C rate. For example, we talk about the amount of current being supplied to the cell or the amount of current being taken out from the cell. If it is very high, then capacity degradation is much faster. And if it is optimized, if it is within a certain limit, then we can observe by just by modeling, we are able to observe how the capacity degradation gets affected when we go on changing the amount of current. Then we have variation in internal resistance. So this again comes under the same topic for age. So this is another aspect studied when it comes to aging, and specifically this reveals the degradation of the internal like materials, like you can say the cathode, the anode, things like that. Because when we talk about internal resistance, it's basically these like major materials that contribute to it. So all these can be studied like utilizing a cell model. So once again, it depends upon what approach we choose. Then we come to the necessity for testing. So basically, development and testing both. So let's say that we do not have a model. If we do not have a model, then it is kind of impractical because we have to develop a battery pack and then test it for each and every available scenario, which is like very much costly and very much time consuming. So, in order to basically ensure that such heavy amount of expenses are not there. So every time developing a prototype of a battery pack and then subjecting it to so many different situations may not always be a very likely or a very practical outcome. So that's where our cell models and battery pack models are very much advantageous, because you can subject these models to any type of environment and they will show you within 90 to about 95% accuracy uh, how the cell and the battery pack behaves. Then you can utilize them in more advanced scenarios by integrating them into battery management systems. So to basically monitor the cell's condition. So not only health, but also temperature, energy, how much power, number of cycles, what is the in terms of cell balancing as well. All these things can be uh, very effectively modeled utilizing a cell model, right? So the final point is energy utilization. Okay, so that is the end goal. So how effectively we are utilizing the battery's available energy in given any scenario that we have, any expected scenario. So it could be thermal, it could be environmental or electrical, safety, failures, etc. You can basically simulate all this and implement any strategy utilizing any algorithms or programs utilizing the cell model. Okay, so this is basically the necessity of cell modeling. So this is why we do it. So that brings us to the approaches of cell modeling, because as discussed before, what kind of outcomes we desire, that is based on the approaches that we choose. So there are three main like approaches that that is like kind of popular. You can say this like very much looked into in this industry, EV industry. So what are the approaches? So the simplest one, so as discussed much earlier, it is called as an equivalent circuit model, okay, as abbreviated as ECM. So equivalent circuit model is basically a representation of all the electrochemical processes within the cell as electrical elements. So you have so many electrical elements that can represent each process, like diffusion or transportation or intercalation processes, and so many complex processes. You can simplify them into electrical elements. We will see that approach in the next slide. So then we have impedance-based model. So basically, impedance-based model is very similar to equivalent circuit model. The approach is different. That is, you are utilizing AC current over here to model the entire cell. Okay. So basically, it is that all the electrochemical processes can actually be separated out utilizing AC current. So if you supply some AC signal, suppose a very small magnitude, high frequency AC signal, if you supply it to the cell, then we get an AC voltage response. And it is from this that we get what is called as impedance. So normally we would refer to it as internal resistance, but in case of the impedance-based model, we refer to this as AC impedance. So there is another approach that is the impedance-based model. Then we come to the electrochemical model, which is the most advanced type of approach. So basically, you will consider the cell with all the materials, that is the electrodes, anode, cathode, electrolytes, the current collectors, the separators, the additives, the binders, etc. And you can model them utilizing what is called as partial differential equations. So we will have a very brief overview of this in the upcoming slides. Since that is not our focus, we will not focus much on the third type of approach, right? So these are the three main approaches that one could consider when we are going for cell modeling. So of course, there are other types where we are going for even advanced modeling, where we are including thermodynamics and things like that. So that becomes what is called as multiphysics. So multiphysics, like you can use COMSOL multiphysics, where not only electrochemistry, but even thermodynamics and corrosion rates, the outside part, the way the cell behaves on the outside as well, how the cell could perform in different pressure conditions, humidity, electrical charge concentration on the outside, static electricity, all those things can be modeled using multiphysics software. Okay. So these are the main approaches. And we begin with our focus for equivalent circuit model, because PNGV model is actually a part of equivalent circuit model. So it is like important to see which part of the cell is modeled how. So if on the left side, you can see there are different mechanisms, like um, basically the major mechanisms are being shown here. There are actually many more, but the major ones that are most relevant for the modeling that will be shown here. So reduction reaction, oxidation reaction. So together, these are the main governing reactions of the entire cell. Okay, these are the main governing reactions. These are the ones that produce electrons so that they can power any equipment. Then there are other ones, like some processes are there which are like a little less major there, but they still contribute to the functionality of the cell. It is called as intercalation and deintercalation. Basically, it is the movement of ions into and outside some of the material. Like you can see on the diagram below, there are like different segments like anode, cathode, electrolyte, things like that. So when an ion moves from the anode into the electrolyte and then into the cathode, the specific movement of the ion into the cathode is called as intercalation. And when the ion exits from that material, it is called as deintercalation. So this way, this also contributes to the mechanisms within the cell, and then there is diffusion. So diffusion is basically the complete absorption of the ion into the internal structure. So you can see very small gaps over here within the structure. So these gaps basically are meant, they are provided so that the ions can sit there and get converted into atoms. So that is diffusion. And you can see on the right hand side how each part, or you can say how each process has been sort of like simplified and represented into electrical elements. The idea is that we are simplifying all these processes, and we can use like electrical equations to just model the entire the voltage behavior within the cell, right? So you can see there are different regions. So there is region 1, which corresponds to what is called as the cell material that contributes to what is called as ohmic resistance. So this was discussed earlier on in the session. So now we see ohmic resistance, right? And in an electrical element, you can just directly use a series resistance like this. Okay, when we're developing a circuit, when we're developing the electrical model, the first element that we can use is a series resistance, which is given by the symbol R0. So then that is basically all the materials, namely the electrolyte, the semi-solid, or you can even call it as a fluid electrolyte, since in most cases the electrolyte is a fluid, not completely a fluid, it is kind of like a paste. So it also has some level of viscosity and it has some like conductive resistance and things like that. So because of its own physical properties and along with other bulk materials within the cathode and anode, we represent that resistance using R0. Then we have the other type of resistance, which is purely electrochemistry related, or you can say like because of the reactions. So these reactions are represented utilizing the combination of this region 2. Okay. So if you observe in this region 2 that we see in the diagram on the left side, we can see like some ions are spread out. Like on the left side, there is positive, and then on the right side, there is negative and things like that. So when there is this movement, when we talked about intercalation and deintercalation and diffusion, these are all purely chemical reactions related. So when there are reactions occurring at the anode and cathode, or when there is movement of ions between the anode and cathode, we will represent the resistances affiliated with these processes as a pair of resistance and capacitance, right? So this is basically modeling the resistances encountered during the interactions. Like there are many things, like there is charge layers. You can even call them as charge concentration layers. There are surface layers. Then apart from this, there are like films, okay, thin films, which are like made out of some insoluble compounds. And all of these basically combined together, they contribute to the chemical resistances, right? So that is how we represent the chemical reactions related resistances, utilizing a pair of R and C, that is resistance and capacitance. So capacitance, because there is it's something to do with the charge. There is like certain accumulation of charge within the anodes and cathodes. So that will be represented as the capacitance C, which you can see here. And the resistance R1 has to do with the diffusion. So when the ions move, intercalate, and also diffuse into the physical material, then they're undergoing some like interaction with other ions, and they also participate in some of the reactions, and because of that we have something called as polarization that happens, right? So this polarization can be actually split into multiple branches of resistances and capacitances. Like you can see here R1, C1, and then again combine this with an R2 and C2, and then so on till such time anyone is satisfied that all the processes that are required to model the cell have been represented here, right? So it could be basically any like n number of combination of resistances and capacitors to get the complete cell model ready, right? So which is where we come to some of the very simplest approaches of cell modeling, that is internal resistance model and 1RC equivalent circuit model. So these are the most, you can say, simplest, or basically some of the most basic cell models that you can find when it comes to equivalent circuit model. So the first one is a RINT model, or what we can abbreviate as an internal resistance model. So whatever we just now talked about, the bulk materials, the chemical reactions, the surface layers and films and things like that, all of that can be combined into just one simple resistance R0, and you can model basically the entire battery as just a combination of your source voltage right? And then which is connected in series with this resistor R0. Okay, so then you model the terminal voltage of the battery just like this. So using Ohm's law, V terminal is equal to I, that is the current in the within the cell, into R0, that is the resistance considered over here, right? So how do we obtain R0? R0 has to be obtained experimentally. So there are many ways of doing that. So that is a very simple approach. It's very much linear. There is not much dynamics being represented here. The mechanisms aren't really being considered. We aren't representing things like polarization and all that, right? So this only considers the complete bulk resistance. That's pretty much all it considers. But when we come to a more advanced approach, or at least we can say a slightly more advanced and more higher fidelity model, so we can consider the 1RC equivalent circuit model. So the equivalent circuit model is derived from the same thing that we described in the previous slide, that is to represent all these chemical processes utilizing a pair of R and C. So you can see on the left side, in addition to the ohmic resistance, we have a pair R1 and C1 that represents the polarization that was discussed. Right, so this is basically to do with the chemical reactions. So apart from considering bulk resistance, we are also considering one of the most important parameters, that is polarization. Okay, so R1 has to do with the resistance that is called as polarization resistance, and C1 is also called as polarization capacitance. Okay, so if you consider the terminal voltage, it's once again it's kind of direct. We just have to consider the voltage drop across R0 and voltage drop across the RC circuit. Okay, so this can be simplified. I mean, this can be obtained utilizing Kirchhoff's current law. So Kirchhoff's KCA. Okay, so KCA basically is Kirchhoff's current law. It's a direct derivation from this. So once we utilize these laws, we can use Kirchhoff's voltage law to then say terminal voltage is equal to I into R naught plus VRC. Okay, so that is how we get the terminal voltage and then model the circuit's behavior utilizing these equations, right? So we also talked about impedance-based model. So a basic review on this. So this is called as Randall's model. So Randall's model basically considers what we know as impedance. And impedance is derived from like AC AC signals. So if you provide an AC input, we get an AC output. Uh, so this model basically splits all the chemical processes that was discussed very briefly earlier. So it splits up all of this into individual segments, and it is able to basically point out that at this frequency, at this magnitude, we get a certain process, and then we can identify that as either diffusion or polarization or charge transfer or intercalation and deintercalation, interaction with other ions, the interaction with electrolyte. So all this can be segmented out, and they can represent all of this utilizing a equation called as terminal voltage due to impedance, right? So instead of considering resistance like how we did earlier, it is now going to be represented by Z which is representing your impedance, right? So there are more sort of not exactly standard electrical elements. We don't directly use capacitors over here. We use what is called as non-standard electrical elements. Okay, so basically the things like imperfect capacitors, Warburg capacitors, those kind of elements are used here, which are much more advanced and usually require like knowledge on things like Nyquist plots or Bode plots, and from there we get all these parameters. So then we have the most advanced approach, which is the electrochemical model, and this is purely to do with the chemistry of the cell and the differential equations that is used to represent all the behaviors, right? So we talked about diffusion, we talked about uh, the charge transfer, or we talked about the movement of ions within the cell. So all that can be represented over here. You can see the equations. They are all partial derivative equations, and it requires a very advanced computing system to get all these equations solved. Okay, so this is a very basic overview of what are the types of approaches we have. So now we move on to the concept that we have to focus on today, that is the PNGV model. So as we elaborated PNGV earlier, PNGV stands for Partnership for New Generation of Vehicles. So this was proposed in 1993, and this is basically a slight improvement or an advancement to the 1RC model, right? So 1RC model, we saw there was only a R naught, and then there was a parallel branch of R1 and C1. So along with this, we also have a capacitor, an additional capacitor in series with the ohmic resistance. This represents the change in cell open circuit voltage as and when the cell goes on discharge. Okay, or rather you can say the influence of discharge or charge on the cell's OCV. So how do we model the cell's OCV in so basically how do we model the cell's OCV as and when the cell is under operation? So either under load during charging or discharging. So this capacitor C naught actually models that change in the cell's internal potential, right? So um, there are like some advanced electrochemical processes affiliated to this element C naught. So we have to go more into the electrochemistry part to understand that. But on a surface level, it is important to know that some small amount of charge layer and charge buildup influences the changes in like open potential. Okay. So you can see the entire layout over here of the model on the left side, right? And now we can just derive its equation. It is very simple. So naturally, when we consider Kirchhoff's voltage law, we say that the total voltage across the loop should be equal to zero, or the sum of all the voltages inside should be equal to zero. So we say V terminal, this is what we need. V terminal is equal to the open circuit voltage, which is theoretically the like the most ideal voltage of the cell, minus all the drops across all the elements, right? So that would be VR naught minus VC naught minus VRC, right? So this is the like simplest way we can represent the voltage behavior utilizing the PNGV model. So how do we obtain each of these values? So VOC is obtained utilizing what is called as an open circuit voltage test. So we have to characterize the cell by performing some like open circuit voltage testing, where you can take the lithium ion cell and attach it to some sort of like passive load, like a cell testing machine, which usually has a passive load. And from there, we can derive the change in its internal voltage with respect to SOC and things like that, right? The profile of the OCV minus the internal voltage drop due to the R naught. So that would be modeled as I into R naught. So directly minus V into C naught. So this is basically the voltage drop across a capacitor, which is given by 1 by C naught into integration of the current I, right? So we know that the current across the capacitor is basically equal to C into dV by dt, right? So the C would be your capacitance, which is utilized in this model. So if you rearrange the equation and say dV by dt is equal to integral I into 1 by C naught, then we get this voltage drop here minus VRC, which we solve utilizing the Kirchhoff's current law. So Kirchhoff's current law. So basically we know that the current across the branches R1 and C1, they change. So they become as I2 and I1, right? So now utilizing I1 and I2, we can drop the total potential difference across this RC branch. So again, we know that the potential difference across R1 and across C1 is the same. So utilizing that, these two constraints, we can derive the total potential drop across the RC branch, right? So in short summary, the equation that we need is here. So now just an extra element, that is this one, gets added to the equation that we noticed for the 1RC model that we had seen earlier. So this can be implemented into the Simulink model. Okay. So basically the PNGV model equations that we have just now derived, they are over here. So this is your terminal voltage equation. And now we can model this utilizing Simulink and MATLAB. Okay. So that brings us to the overview of a Simulink model. So which I will show you here. So you can see in this particular page, this particular model of Simulink, we have all of the important components required to model the total terminal voltage. Okay, so one by one we can see what is inside this. So we begin with SOC estimation. So SOC estimation is done utilizing a very basic approach that is called as Coulomb counting. So that is the integration of current with respect to time. Then utilizing the cell's capacity as a reference, we get the SOC as output. Then we have open circuit voltage. So based on the state of charge, we again get the OCV as output. So this is the first parameter that is estimated here. Then we come to internal resistance. So again, the same thing, we use SOC as an input, and then we get the internal resistance, that is R naught, right? So this refers to the parameter R0. Then we have polarization resistance R1. So again, you're usually utilizing SOC as the input, and then we get the first RC branch parameter, that is R1. And then from here, we get capacitance C1. So all of these are fed utilizing what is called as a lookup table. So you can see here that this is a single dimension lookup table. So lookup tables are very useful when you want to simplify the modeling approach. So we basically use a table that looks like this. So inside this lookup table, we can actually see the variation of the capacitance C with respect to state of charge. So yes. So this type of approach is very simple, where Simulink does some like interpolation at each point, and based on the desired input, we get the desired output. So this is just an example. So this happens for all the elements that we utilize within the model. So it could be R naught or it could be OCV. So all that is mapped to utilizing what is called as a lookup table. So that is the approach of modeling. And just as we saw the equations now, we see that the total terminal voltage is now being represented using the equations that we have derived for the PNGV model. Okay, so this is the terminal voltage estimation, like the subsystem. And now we can like just have a quick view on how the model simulates. So after having simulated, like you can see there are two graphs. One is pertaining to the state of charge, and the other one is pertaining to the terminal voltage, right? So the terminal voltage here is like, of course, it is calculated after like having all the losses. So we can visualize the same thing even in the like MATLAB like editor in the workspace. So we can see here that the same data actually has been logged in the MATLAB workspace as well, right? So now here what we are doing, we are comparing the simulation results with that of the measured voltage. So this measured voltage, this comes from the static capacity test. So there is something called as a static capacity test. Right. So this static capacity test gives the available discharge capacity of any lithium ion cell. And in this case, like it has been rated to be 5 amperes, 5 ampere hours. Okay, so 5 Ah is the capacity of the cell, and then you can see the red line. The red line is the one that corresponds to the measured voltage, and the blue line is your simulated voltage. So basically, this is for the PNGV model that we see here. Okay, so this is how we can like simulate a simple PNGV model utilizing some like data-driven approaches. So overall, this equivalent circuit model is also called as a data-driven approach because it relies on some external data of the cell to model some behavior, like some fundamental data is required, some basic data is very much necessary. So this is obtained from like different tests, like as mentioned before, the static capacity test and other tests like DCIR, the direct current internal resistance tests, and things like that. Yeah. So that brings us to the conclusion. So with respect to the model simulation and development, so we can conclude like some of the important points here. First one being that how effective is your PNGV model? So PNGV model is one of the most effective and like you can say computationally efficient models because we don't have to rely on large amounts of data sets to model the cell behavior. So as described before, we can model the entire electrochemical reaction utilizing the R and C approach. Then already your ohmic resistance is being represented there along with the capacitor, which talks about the like change in your OCV with respect to the application of load. So that is the one of the important conclusions we can make. And since it was introduced already by like three large OEMs, we can say that like they're also very much reliable in representing real-time cell behavior. So of course, we can also conclude that this cell model still like we can expand this into electrothermal model where we can combine the temperature estimation approach and things like um, the SOC and SOH approaches as well, where we can modify those and integrate this into a more, much more sophisticated model. So yes, this model is very much versatile. You can use this in many approaches and like you can utilize this satisfactorily with very good results. Okay, so here we can see just that a very simple scenario has been presented. So there are many more simulations which we can do where we can conduct a pulse discharge and a pulse charge simulation as well. So this is basically what we supply as an input. This is what we, so this is the input. You can see here this red line corresponds to the current. So you can supply a pulse current as well. And then you can get the voltage response, which is at the bottom. This voltage response will be recorded once again from the measured data. So from there, we can actually use it as a reference to go for cell modeling as well. And then we can see how close the PNGV model actually represents this kind of behavior, right? So of course, there are also more advanced types of modeling as well, where we can go for simulation in real-time scenarios where we have drive cycle inputs, and from there we can get outputs as desired. So this is the conclusion that we make for this PNGV model. So thank you for your time in this bootcamp.